So instead of starting with the lecture tonight, I'm going to actually start with, hold on one second, just writing down some information with a notebook, and I'm hoping that you can see it. So I wanted to talk, before we talk about transmitting with serial I/O, I want to talk about what are we transmitting, and we want to be able to transmit data. And so typically when we talk about transmitting data, we're talking about transmitting digital data, which normally means that we're going to be wanting to transmit something that in the end looks like zeros and ones. But first, let's just say that we are going to start with just regular numbers. And so I want to talk about what is decimal, what is binary, what is hexadecimal, and then what is ASCII, all those differences. And I'm sure many of you have heard all of those different terms, but maybe you don't understand exactly how those relate to each other. And so when we start talking about what we're transmitting, we should go over those identify what each of those are. So I'm just going to start right now with what we all know whenever we write numbers as decimal. And I'm just going to go ahead and write out all of, I know it's going to be a little hard to see here, and just bear with me while I write all these numbers down. You're like, I know this, what are you doing? But that's all right. Okay, so that's whenever we go to 16, those are the numbers that we typically think of, and that's the decimal system. But if I were to write this in binary, we think of binary as, if we were to look at it on our scope or just think about it, we basically, say we have a 5-volt system, and then we can transmit to 0 volts. And then this is our time axis here. Then whenever I say, if my signal is at 0, then that's typically what we call a 0. And when my signal goes up to 5 volts and comes across and down, we say that at the time, this is transmitting a 1 or a high. And when our signal is here at the bottom, we're transmitting a low or 0. So it's like a switch. You turn it on, off. It's 1 or 0. That's what we say when we think about binary. And whenever, if we're going to write binary, if I were going to write these same decimal numbers, let's just go through it. So I just told you that it's a 0 and a 1, right? So if I were to write binary, that it would be the same as decimal. But then whenever we get to 2, we've run out of bits already. And so, by the way, whenever we say 0 or 1, that's what we refer to as bits. So if you hear bits, a bit can be represented by a 0 or 1, and those are the only two numbers that a binary number can be represented with single bits. But we can go to bits. So I can come here and add this, and now this is what 2 would look like. And then the same thing with 3. And then if I want to represent 4, oh well, we're out of bits again. So now I'll add another one here, and it's 1 0 0. And I'm just going to go through now and fill it in. And then 9, 10, 11, 12, 13. And by the way, this is all online, so you're welcome to go look up these tables, and I'm going to show you exactly some other ways to take a look at this. And then when we get to 16, we would need to come in and add the other 0 here, and then that would be 1. Okay, so whenever we're talking about binary, if we wanted to represent those same numbers in decimal, it would look like something like this. And I'm not going to go too much more into detail. There's a lot of information on this. And actually, I'm not sure if this has already been covered. I don't think it has, and this might get covered again at a later point, but for today's lecture, I thought it was important. So there's also something that uses, instead of base 2, or it uses 16, and that's called hexadecimal. So now whenever we're representing hexadecimal, these same numbers are going to look a lot like decimal, but then it's going to change. And you get from 0 to 9 all looks the same, but then you go to A, B, C, D, E, F. And so it basically, everything from 0 to 15 is represented through one loop of hexadecimal. And then whenever we get to 16, then you have to go in and you kind of start over again, and you do the same thing where these all become 0. Okay, so I just wanted for everybody to sort of see that. Now, whenever we are talking about, another term that you might have heard of is ASCII. And so I'm going to show you, so whenever we type things on a keyboard, we are typing in ASCII. It's ASCII characters that are being transmitted to the microcontroller of the computer, and vice versa. So I'm gonna show you a website. So I'm gonna pause this real quick, and then come over. Okay, so I'm sharing this, and I just did a Google search for ASCII table, as you can see here, and then let me just show you what it looks like. So you can very clearly see here that we're showing in decimal, and then hex, and then these are all the different characters that are on your keyboard. And a lot of times you'll also see binary represented here. I grabbed a website that didn't have it, but it might show it as well. But if we actually look at the numbers, you can see that these correspond to something in decimal and something in hex. So, 1 corresponds to 31, and then the same thing with all of these. And so later in the lecture, there's going to be a discussion about the letter S, and I just wanted to point out that this is where the hex number comes from, is 53, and then the decimal number of that would be 83. So hopefully this sort of can help kind of make sense. And so again, ASCII is used to display things on your monitor with input from your keyboard. So if you want to send an ASCII character to a character to a monitor, then you need to make sure that you're using ASCII. And then whereas within microcontrollers, sometimes you can denote numbers as decimal or binary or hex. Those are the typical things that I have used. So you just want to make sure you understand what numbering system you're in and you're displaying information at. So, okay. So the point being, if you send a decimal character to be displayed, if it's denoted as decimal, but you send it to your monitor, then basically it may not get displayed properly. So, okay, I'm gonna move on to the lecture now, but I just wanted to share that. Okay, so as I mentioned, we're going to be talking about serial I/O today. If you remember, I/O stands for input and output. So again, we're trying to transmit data, which ultimately you're going to see is going to be represented by 1s and 0s, which are bits. And serial communication sends one data point at a time, as opposed to parallel communication, which sends multiple data points at once. And so we're going to be talking about those two different concepts of serial versus parallel. So in a serial interface, you have the device, and then you have the second device, and you're trying to send information between those two devices. So that's again, we're trying to transfer data. We're trying to transmit it and or receive it. So typically you'll have a data in and a data out, and then depending on how this device is configured, you either need to be sometimes these are connected the same, we'll see that, and then other times you might need to cross the transmit and receive. So just be aware of that. Typically you'll also have some kind of control line and clock that's associated with these two lines. So asynchronous signal, or serial, can be implemented with data lines only. And so importantly, that means that each device generates its own clock, So you don't have a clock line. And that's, you can see it, example is a baud rate generator. And then handshaking lines can also be used to signal the status of devices. A synchronous serial interface will have a separate clock line. So the clock is generated by a master device. And then 1 bit is transferred for each clock cycle. This is the opposite of this, or a different, it's not really the opposite, it's just a different interface, is a parallel interface. And so again, we see that there's a device 1, typically there's a master, and then device 2 is might be a slave. And the same thing with there could be a master and slave device as well with the other serial interface. So you might see that again come up. But instead of having all of the data transmitted on one line, we now see that each hardware line, again, whenever we're showing these lines, these are literally some kind of wire or copper trace that goes between these 2 devices. So in this instance, there's 7 or 8 data lines. And we also see here something called LSB and MSB. And so just remember that LSB is the least significant bit, and then MSB denotes as most significant bit. And I'll show an example of that on one of the other slides. They have it. But basically, at the same time, these are going to be clocked usually. And then for every clock cycle, there'll be a bit transmitted on each of these data lines that will then be read in. And then you also tend to have this RW, which is the read-write clock cycle. That's another hardware line that will have to be selected to say, hey, this is a read or this is a write. And then CS is typically chip select, something called chip select. And whoever made this presentation has this line above these. Whenever you see that, that's usually an inverted logic. So normally, like if you think of like turning a light switch on, or that you're going to supply power to something, right? But whenever we think of inverted logic, in order to get that whatever we're working with to turn on, it actually needs the opposite of like a ground rather than power. So the data lines may be unidirectional or bidirectional. The width of data is usually 1 byte wide. So that's another word that you probably have heard often is byte versus I've been talking about bits. So a byte is 8 data bits. And then to go further, if you've ever heard of a data word is usually 2 bytes or 16 bits. And then a full byte of data is transferred on each read or write clock cycle. Again, chip select allows multiple devices to share a bus. So for Arduino Mega, so we're going to be talking mainly about the serial communication on this device since we're all using it. The serial hardware communicates via electrical pulses that represent 1s and 0s. Again, I just mentioned that for the Arduino, from what we learned before, I was reading today the data sheet, and it said that it operated on 5 volts. So to me, that tells me if I look at that signal, when I look at a data signal for the serial bus, if I see a 1, that should be represented by that logic. A logic 1 should be represented by a 5-volt pulse, and then a 0 is going to be represented by a ground pulse. And then the Arduino uses a universal serial bus, which is just a regular USB. So a USB is also a serial device that communicates and has a specific protocol. And it connects to the serial hardware. So that's what you've obviously, if you've worked with this already, you've plugged it in, that's a USB. There's a note here that says serial communication is also possible via software libraries, but this is not as efficient. And then the Mega has one that should be, I'm not sure if it's USP or USB port, if that's a different protocol, and 10 serial pins. So point being is there are many options for you on this board to have different serial ports. So it's important if you want to communicate to multiple devices with different serial ports, then you have the opportunity to do that. So synchronous means that the devices involved use the same clock signal when communicating, while asynchronous means the devices use their own individual clock. And pins 1 and 14 through 19 are what's called a UART, or Universal Asynchronous Receiver Transmitters, for the asynchronous communication. And yet no two clocks run the same, so asynchronous communication is slower because extra data must be sent periodically to ensure both devices are in sync. So serial communication usually involves sending or receiving characters using the ASCII code. So we just talked about ASCII, and we're talking about, and when we're talking about ASCII, we're talking about characters, such as those that are on your keyboard. And so, for example, the character S is represented by the binary number 01010011, or 53 in hexadecimal. So if I just look at, I'm going to just do a quick, another screen share here with, back to here. So we said that S, our letter S, was represented by hex 53. Oftentimes, by the way, you'll see hex written as 0x53H or something. If you see it in code, a lot of times you'll see that. I'm sorry, my 3 looks like a 5, but they are different. So if I come back over here, and we saw that long number that was in binary, and we're like, where did that number come from? Well, if you look over here, here is 5, and so that's 0101. And then if I look at 3, then that's 3 right there. And so it's 0011. Okay. So that's, I believe, the number that we found back in this presentation. Right here. So it is. So whenever I see 53, then I go and look at the bytes, or the bits here, and then I look at the first 4 of them, and that tells me what that first number is. And then the next number 3 will be the last 4 bits. So that's the easy way for you to be able to read it. Also, let me see if I can get it here. Hold on one second. We're going to stop this. I'm going to show you in the calculator that comes with just the regular Windows calculator. Let me come back to this screen. You'll just have to do this a lot, so that's why I'm spending a lot of time on it. And again, I'm not exactly 100% on how the Arduino works, but the other microcontrollers I've used, I've had to switch back and forth between this. So if you look here and you just go to Programmer, then we can also type in all these different things. So if I wanted to go to hex, then do you see how all the letters now appear? But if I say 53, then that's going to tell me what it is in binary, and it's also going to tell me what it is in decimal. And then octal is another one that goes on the base of 8, of the number 8. So it's really nice if you're confused about something, just open this up and then go to the menu, and then you can see the programmer calculator right here. And then you can just switch back to the regular one if you need it. But and there's some other things on here that you can play around with, but it's really nice. So let's just say that I instead I wanted to show a number that was, so if I go into like FF, then you can see that the decimal is 255. So this is going to also be important to know how, whenever we start talking about precision and about 8-bit versus 10-bit on like the analog input and different things like that, how these things start overflowing, you'll start taking a deeper look. But for now, this is good. So hopefully you understand how to switch those things around. Okay, so now we know where this number came from. Okay, so we want to transmit an S, right? And so an asynchronous transmission of S begins with a start bit, followed by 8 data bits, and ending with a stop bit. And there are numerous options for data, for number of data bits, speed, and optional parity bit. Okay, so if we look at the bottom of the screen here, let's take a deep look at this. So they kind of have this green plot here that says bit time. So you can kind of think of that as the clock. And then this idle period. So again, imagine that this is the communication going across a wire between two devices. It's a single wire, and one of them is just basically holding what we call holding the line high. And so it's doing nothing, it's idling, it's holding at 5 volts right here. And then it decides, hey, I want to send some data. So it's going to, what we call, pull the line down low. So, and it has what a start bit. And then the line goes back high, and then it starts transmitting data. And so there's the 1 1 0 0 1 0 1 0, and then back to the idle state. So remember, on the previous slide I mentioned something about a MSB and an LSB. So we're talking about most and least significant data bits. So whenever I look here, we see that the 5 is the 0101 or 0101, and then the 3 is the last. So when I look at this, the 3 is the least significant bit, and then the number that's over here is the most, or the bit that's over here is the most significant bit. And you can see that it is transmitting the most, in this particular instance, because this is the time axis, that it has transmitted the most significant bit first, and then it's transmitting the least significant bit last. So whenever that's like, it's very important to know how, for the built-in functions, like what we're going to be using for the I2C bus, it's going to do all of this for you internally, because there's a standard for I2C that the people that design these systems know what it is, and so they always use that standard. So it's not super important, but if you were to ever take a digital output and create your own signal that's going to communicate with something else, you need to be aware of how that other device needs to look at the data. Does it need the most significant bit first, or does it need the least significant bit first? There's different protocols for that, so make sure to look at that. Okay, so again, the Arduino is really nice because it has these great built-in functions for you. So you don't have to worry so much about the details of what you're sending across, or like how all of the underlying things that need to go on in order to send serial data. All you have to do is set up the serial port, connect the wires, and then you're able to use these commands where you can say, read a byte off of the serial port, or transmit, I don't see it, or write, if you want to write something. So typically, whichever one of those interfaces you're using, take a look at these functions available, for that particular serial protocol, because there are several on here. And then you're able to basically write functions without having to worry about all those little details that are happening underneath. Other than you need to make sure that you are, if you're writing to a display or whatever, that you're using the hex or the ASCII, hex, and binary. And again, some of these functions might already be converting it. I know the ones that I was playing with earlier, it seemed like it was like, if it knew that it was writing to a display and you put something on there, I think it automatically might know that to convert it. So, okay, extra serial ports. So the Arduino Mega has 3 additional hardware serial ports. Serial 1 on pins 19 and 18, serial 2, and serial 3. To use these pins to communicate with your personal computer, you'll need additional USB to serial adapter, as they are not connected to the Mega USB to serial adapter. So it's possible too that there you might be able to use some other protocols for that as well, other than not just USB, but that is nice they have that. And then synchronous serial I/O. The synchronous serial I/O uses a separate line for a clock signal. Yeah, so that's important. The synchronous serial clock data lines in Arduino all use TTL logic levels, so no level converters or line drivers, receivers are required. Okay, so what does that really mean, and what was the previous one? So again, whenever we are hooking up two devices, we need to ensure that those voltage levels match. So I was just saying that, you know, whenever I looked at the data sheet, this particular device uses 5 volts logic, or operates at 5 volts. So if I wanted to connect it to a different device, so that means that if I'm going to communicate on a serial bus, that it's going to transmit those ones and zeros using like 5 volts. But then maybe the thing that I'm communicating with really wants 2 volts or 3.3 volts or something else, then you have to add in an extra chip. IC that, like such a line driver receiver, that's going to do what we call level shifting, so that basically those voltages will match on the two sides. And you can burn up other chips if you don't pay attention to this. And this, again, I think will be really important later on whenever you start designing your own systems. Make sure that you are reading those data sheets. And sometimes, even though a part will operate at a, like maybe 3.3 volts, it'll say the serial port is accepts 5 volt, you know, communication. Sometimes they have that, but sometimes it's not, and then you basically you'll start putting in some higher voltage and damage the other chip. So that's what that means. So there are several protocols in use. Some use a bidirectional data line, while others use separate data in and data out lines. The master generates the clock and initiates and controls data transfer. So let's look at the diagram here. We have the Arduino Mega. We've got the clock going from the Arduino to whatever it is, this other chip that's communicating. And then you've got the data out and the data in. This is called what we call full duplex. Whenever you basically got the clock with two separate, like you've got a transmit line and a receive line. It's basically what it is. And then there's also this type where you've got the clock, but a bidirectional data link. So you can see whenever we have two arrows here, that means that those pins, like that, even though it's a single cable or a single wire, that the device is set up where it can both transmit and receive on the same line. So what's important here is that you can see there's one less wire that's required in this one versus this one. But what it also means whenever you have this is that there is what we call overhead with the software. And that's because you basically, in one instance, when the Arduino Mega wants to transmit or receive, it can just blast out whatever on this line. It can send the clock and then it can just blast the data out. And this guy is just willing to accept it. And then if this one wants to communicate, it just has its own dedicated line. And so it's really just like a pretty basic transmitter receiver signals that are going to be coming there. However, with this one, because this is bidirectional, now when this one wants to communicate, it has to say, hey, I'm going to take the data line and I'm going to communicate with you. And then this one has to send another bit back that says, okay, I'm ready. And then it's going to go back and forth. And we're about to see an example of this exactly. So I know the last slide is specifically talks a little bit about this one here. This in this format is typically called SPI, which is Serial Peripheral Interface. And so sometimes you are going to find IC chips that you're going to want to use, and they're going to say it's an SPI chip for the data communication. And then this type is typically called I2C, and so that's the protocol we're going to be working with tonight. But some of these devices that you might want to start using might have both interfaces. Sometimes you'll see both, but sometimes you'll see one versus the other. And it's important to understand sort of what those differences are. So one basically can be sort of faster because there's no software overhead, whereas the I2C is going to be a little bit slower, but I'm going to show you some of the advantages that you can get because you don't have those extra hardware lines. Okay, so the I2C bus, some people say I2C, I prefer I2C, either one works. And it is a synchronous serial protocol that uses a bidirectional data line, just like we talked about. and supports multiple slave devices controlled by an I2C bus master. So it was defined by the Philips Semiconductor and became an industry standard. So now it's implemented in a lot of different chips. And there could be different protocols that you might come up with, or other companies have come up with, but it's a matter of this one is very popular. So it has become accepted and used. And then other companies start using that same protocol, and then everybody's sort of using it. Okay, so important here is the clock line is called SCL, and then the data line is called SDA. And so you can kind of look at that CL, and that's how I always just know. It's very simple, like it's clock. That's very clearly clock. And this one looks like data. So that's, when you look at that, you don't typically have to question that. And there's the I2C master, which in our case is going to be, in activity, it's a little different tonight, but typically this will be your the Arduino or whatever microcontroller you're using. And then you're going to have the devices here, device 1, 2, 3. And then you'll see, so these, whenever we have multiple devices like this, the beauty of I2C is that we can do what's called daisy chaining. So daisy chaining means that they're all sharing those same hardware lines, but we're all able to communicate together. So importantly is to look at how this is connected. So we see that SCL is connected to SCL here, SCL here, SCL. And then the SDA is connected also to all of the same things. If we were to use a system like the SPI, and I'm just going to again point this out briefly, there's a brief slide on the end, but it doesn't really point this out. But also this is true with just a regular UART that you might be using, like that generates its own baud. Whenever I see data out and data in, and then I look at these arrows, this is in respect to the Arduino Mega, but it is not in respect to the serial IC. So that means that this one, whenever I hook up the lines, this is typically a transmit. This needs to be connected to the receive line of this one. And then this data in needs to be connected to the transmitter side, and then it'll be in the receive side here. So we call that crossover. You'll have to cross the cable over. So that's really important. Fortunately, with I2C, that's one nice thing, is you just connect them all to the same pins. And you also don't require separate pins. You these things, they also don't require a chip select, like what the SPI would use. So with the SPI, you have to have a hardware line just to say, I'm going to talk to you. It's basically you're selecting that chip when there's multiple chips. So it's a digital signal. I'm going to select you. I'm going to select you. In I2C, each of these devices has an address. And so when the master wants to communicate, it's going to come in, and the first thing it's going to transmit is an address, and that's going to wake up one of these devices. So whenever you buy a device that has I2C, you need to make sure that you understand what that address is, and that it makes sense in whatever addressing scheme that you have with all of your other devices. A lot of times they're settable addresses, but you just want to make sure that you can control that. And then also important here is these pull-up resistors. So I have had a design before where we did not have these pull-up resistors. We thought we didn't need it because maybe a device says that it has a pull-up resistor. You definitely need these on the with I2C. So make sure you understand whenever you need to add that. And basically this is what's going to provide all of the lines being pulled up, and then basically all of each of these devices have to do is like sync the current to pull it to ground. That's basically what's happening. Okay. So the I2C bus master generates SCL, which is the clock, and it's going to initiate communication with one of the slave devices. And each device has a unique address for device selection, what I just mentioned. A device address can be a combination of bits that are hardwired into the chip design, or one or two more pins on the device. So like I said, sometimes you have to add some resistors or something to set this. So this is really important if you're ever designing a board or you're about to use a part. Make sure you understand that. These pins can be wired high or low to select an address that doesn't conflict with the other devices on the I2C bus. Pull-up resistors are required on both clock and data lines. Some chips may have an internal pull-up resistors on specific pins. A lot of times now, like even if it might have one, I just add the resistors on the board and then I don't populate them if I don't want to use them. A variety of special function integrated circuits are available with I2C interfaces, including memory chips, analog to digital converters, digital analog converters, and real-time clocks, as well as temperature sensors. So like, just something simple as a digital temperature sensor, those typically can be use I2C. And you can have multiple ones. So if you wanted to monitor an entire system with I2C digital temperature sensors, you can do that with this, and you would only need 2 wires to your system. So more about the details of this. A start sequence begins a bus transmission by transitioning the data line from high to low, while the clock line is high. So, and then a stop sequence ends transmission. The stop sequence occurs when the master brings the SDA. So the master is bringing the data line from low to high while the clock is high. Okay. So again, this is just showing you sort of those details about how this is done. Like I said, we have to have that software handshaking going on so that way the master can initiate all the communication. So I2C write sequence, a typical I2C bus sequence for writing to a slave device. So it sends a start, we're going to go through this, sends a start sequence, it sends the I2C device address with the read write low for write, it sends the data byte, it optionally sends additional data bytes after repeating the start, send the stop sequence after all data bytes have been sent, and then the slave acknowledges by setting the acknowledge bit. Okay, so let's just look at this down here because it's a little easier. So here we are. Remember, again, these are 2 wires going between the 2 devices. On the data line, the master pulls it down. Okay, and then it's like, okay, the first thing it's going to do is it needs to send an address to all of the things that are out there. So that particular device can wake up and say, oh, I'm here, right? So it's going to start, sends all of the bits, and then we have this read write because it needs to say, hey, number 86, I want to write something to you. Or, hey, number 86, I want to read some of your data. And then number 86 is going to come in and it's going to give a little tug on the line that's going to say, I acknowledge you, or sometimes there's something called a NAC, which is does not acknowledge. So it looks like in this case, we got an acknowledge from number 86, so we're good. So now the master is going to then proceed. If it has to receive this acknowledge. So if you ever have something hooked up and then you're only seeing 1 byte being sent or something weird, something's not hooked up right, and then your other device is not sending this acknowledge. So then it will send a data byte here, and then the same thing. Notice there's no read write on this one because this is just the full data. And so whenever I'm saying like, oh, it wants to talk to number 86, what is it? It wants to read something. It wants to read a register, probably a register where like a temperature is stored. So it's going to send the address of that register for whatever information it wants. And then again, the other one, the number 86 is going to send this acknowledge, and then the line's going to be pulled high again, back to idle state. And then if there's more information or whatever needs to happen, then it's going to be pulled down again. And then this is all in reference to the clock. So the clock, typically depending on the device, sometimes you'll see that it's on the leading or rising edge or falling edge. And whenever you see something like that, that is whenever the data is going to be sampled. So the clock is here, it starts here. So whatever that status is, if it's high or low, at the time of the rising edge of the clock, that is when that information is going to be read. Or if it's on the falling edge, then it'll be read on this back side of the pulse. So the clock is important. It needs to sync up to the data, and then you'll be looking always at that rising or falling edge where your data is being lined up with. All right, so I think that's all of the things about this. It's important. And this, you know, we're talking about I²C here, but short of those acknowledge, you know, bits and the start and stop and things like that, this is really how all data is transmitted in some form. It's a great example of a clock where data is being transmitted. Like, this is how you line up the information and it's being read. So reading an I²C slave device usually begins by writing to it, and that's important. You must tell the chip which internal register you want to read. So the I² read sequence, it's pretty similar to what we just talked about, but you send the start condition, send the device address with the read write being held low for a write, and then send the number of the register you want to read, send a repeated start condition, send the device address with read write set high, read the data byte from the slave, and then send the stop sequence. Okay, so it's really important, or like, it's great that we're going over this and that you have an idea about all of these lower details of everything that's going to happen. But again, whenever you start working with the Arduino, it has all of those nice functions that are going to do all of these little details for you. And all you're going to have to do is just send the the information that you want to read from, and then you're going to be able to do it in a function. So don't get too caught up with all the little details here. So it looks like there's now an example of a read example. So this is nice because it actually has some of the data. So we're going to go through. Oh, hold on 1 second, we got it. Somebody chatting. Actually, okay. Oh, it will be. Okay. Thank you. All right, great. So we're going to go through. So this is, we want to look at the device address 11000000 and reading register number 1. Okay. So let's see. The device address is that, and then we're going to read register number 1. All right, perfect. So you can see here, we've got the start, we're pulling it down, and then it's going to come up. So now it looks like in this situation that we are transmitting the least significant bit first, and then actually, I guess maybe I'm getting confused here about the sequence of time with this, because normally this would be the first thing sent out, and then this is the second thing sent out. So, okay, pay attention to that whenever you have to deal with this. I've kind of gone through it. I think I'm confusing myself a little bit with this, but okay. So, but regardless, we can see the data bytes are 1, 1, and then all zeros right here. And then for this instance, there's a read, so that's a low on the end, and then we're going to get the acknowledge, and then we're going to read from register number 1. And so now we're going to transmit register 1, and then it's going to acknowledge it. And then this is, let's see, I think this is the device now responding to it. So now the device is going to send data back, and it's saying, hey, this is still my device address, so it's still going to call itself out, and then it's going to send the data from that address. All right, and then we'll go, and then you get to stop. Okay. So the wire library allows you to communicate to slave devices using the I²C bus. And so the functions available are all of the ones that are here as follows, which is misspelled, so sorry about that. So there is a bunch of information about how to use all of these different functions. So definitely take a look at them and be able to work with them even for tonight for this particular activity. And several IC manufacturers have developed their own protocols for synchronous serial communication. So the data sheets and application notes from the chip manufacturer should be consulted for design and troubleshooting tips. So a popular serial, another one, as I mentioned before, is the SPI bus, serial peripheral interface for Motorola. Again, this is another really popular one that uses the full duplex data transmission.